All right, so what we're going to start talking about now is we'll start talking about sequences. And this is from 2.4. And essentially, we'll start out with the definition of a sequence. So a sequence it's a function from a subset of the set of the integers to another set S. Okay? And so how this basically works is we're going to generally write it as an, okay, equals, and then we'll define it some way, like, for example, as a 1 over n. Okay? And n, right, is called our index. And what it does is that for each value of n that we have here, we're going to put that same value of n into this function. So for example, a1 is going to equal 1 over 1. a2 will equal 1 over 2. Notice how they match, right? Okay. a3 will equal 1 over 3. And then we generally will write our sequence as 1, 1 half, 1/3, 1/4, etc., 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 etc. Okay? We could also have something that looks like this. an equals 3n minus 1. Okay? So then a1 will equal 3 times 1 minus 1, which equals 2. a2 will equal 3 times 2 minus 1, which will equal 5. a3 will equal 3 times 3 minus 1, which equals 8. So notice that what we have here is that our index and the number that we put into the sequence, they're the same, right? And so this sequence would then be 2, 5, 8. The next one actually will be 11. You can check that for yourself, and so on and so forth, okay? Now, let's take a look at an example of one of these, a special one, and that's called the geometric progression. All right. So a geometric progression is a sequence of the form, and we write it AR squared, AR cubed. Okay. Another way to write that is AN equals AR to the N. All right. So you'll notice that the first term, or the 0th term, is A to the 0, which equals AR to the 0, which equals A. Then we'll have A1 will equal AR to the 1, which equals AR, and then so on and so on and so forth. Notice the 2, the 3, etc., etc. And then what will change is we'll change our A's and our R's. So A is the initial term of the sequence, the first term. R is going to be what's called the common ratio, okay? And in both cases, A and R are real numbers. Basically, a geometric progression will be like a sequence where the next term in the sequence is a multiple, positive or negative fraction, whole number of the previous term. So let's take a look at an example like 1, 2, 4, 8, 16, 32. That's a geometric progression as each term is 2 times the previous term. So like, for example, 2 is 1 times 2, 4 is 2 times 2, 8 is 2 times 4, 16 is 2 times 8, so on and so on and so forth. And we can actually see that we have that common ratio. And in this case, our A equals 1, and our R common ratio is equal to 2. Okay? And so that's kind of like how geometric ratio works, right? If we can determine that each subsequent term is just a multiple of the last term, then we say that that is a geometric sequence. Now let's take a look at a geometric sequence, or a sequence for a geometric progression. So let's have this one have a equal to negative 3 and then r equal to negative 3. So an is going to equal negative 3 times negative 3 to the n. Okay? And so we'll figure this out a couple different ways. We'll first say the first term here is going to be negative 3. And then the next term is going to be 9 because that's negative 3 times 9. And then we'll multiply by negative 3 again. That's negative 27. Then we'll multiply by negative 3 again. And that'll end up giving me negative 81, positive 81. So on and so on and so forth. Using our equation right here, we could actually say, okay, you know what? A0, A naught, is going to equal negative 3 times negative 3 to the 0, which equals just negative 3. A1 will equal negative 3 times negative 3 to the 1, which equals negative 3 times negative 3, so that's 9. A2 will equal negative 3 times negative 3 squared, which will equal 9 times negative 3, that's negative 27. And we could actually see that each one of these terms, negative 3, 9, and negative 27, they correspond to the values inside of my sequence. Okay, so basically that's what we do. We could do it one of two ways, right? So like if we wanted the first 10 terms, we'd do this 10 times, right? Here's the first term, second term, third term, fourth term, etc. So on until we hit 10 terms. Or let's say, for example, I want to know what the 10th term is. Well, A10 is going to equal -3 times -3 to the 10th power. And then I would go out and figure out whatever that is. Okay? And that would be my 10th term of the sequence. All right? Now, what if we wanted to determine the function for a geometric progression? That is that we're given the values of a sequence and we want to figure out what the progression actually is. So let's take, for example, 2, 10, 50, 250, 1250, so on and so forth, right? Now, the first thing we want to notice is that the first term is the initial term. So A equals 2. The common ratio is the value that each subsequent term is multiplied by. That each previous term, is multiplied by to get the next term. Multiplied by to get the next term. So what we're looking at there, for example, in this case, we're going to say, okay, well, we've got A equals 2. That's pretty simple. It's the first term. But what we want to do is we want to see that 10 divided by 2, that's 5. What that means is that if I take 2 times 5, that gives me 10. And if to just try it out, right, 10 times 5 is going to give me 50. Great. 50 times 5 is 250. So it looks like that equals R. Now you could choose any two terms. And divide the subsequent by the previous. So for example, we'd see something like 50 divided by 10, right, which equals 5. Or you can choose any one of the terms, and it'll actually give you the same exact values. All right, so we wanted to take a look at what exactly is a sequence, right, and utilize some of our notation. So our notation here, we see this a to the n, and n is called a subscript. It's our index, and then for each value of n, it'll be 1 over whatever that index is. Or in this case, for this sequence, Not every sequence looks like that. What we'll do is we'll just place in whatever value that we have here for the index gets placed into the sequence as the value for n, and that actually is that particular term. Then we also defined what a geometric progression was, which is basically a sequence where the subsequent term is just a multiple of a previous term, right? And we talked a bit about how to determine if the sequence for a geometric progression, and also determining the function for a geometric progression if we're given the values for the sequence. And so that kind of covers what exactly is going on inside of this particular video.